In this lecture, we are going to look at a Colab notebook that does transfer learning with data augmentation. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. It's called PyTorch Transfer Learning with Data Augmentation. So at the top we have all our usual imports. We have one extra special thing, which comes from the Torch Vision library, and that's the Models module. This is of course where pre-trained image networks are accessible from. We have some other minor new imports as well, but you'll see how those are used as we go along. Next, we download the data, which is called the Food 5K dataset. This dataset is a set of images of food and non-food items. So it's a binary classification dataset, and your job is to classify whether an image is food or not food. The next step is to unzip the file. Since there are a lot of files, we're going to use the QQ option to suppress the output. Next, we're going to do an ls to see what got unzipped. As you can see, there are a few new folders here, specifically evaluation, training, and validation. So let's check and see what's in the training folder. So as you can see, it's just a bunch of image files. So what do we know right away? Well, we can see that this is not in the format we need in order to use the image folder dataset object. What we are looking for is one folder for each class of images. What it looks like, though, is that all the images for one class start with a 0 in the file name, whereas all the images for the other class start with a 1. Of course, we shouldn't try to guess whether that's true or not. We should at least do a sanity check to make sure that this is actually true. So let's print an image that starts with 0 just to be sure. So I've chosen 0808, but you should try other images yourself too. Alright, so this is a flower, which is not food. Next, let's try an image that starts with 1. I've chosen 1616. As you can see, this appears to be food. It looks like pizza. Again, try a few other images yourself to see if all the zeros are non-food and all the ones are food. Now, since these images are not organized the way we need, we're going to have to move the files around a little bit. So let's start by making a new folder called Data. Inside this folder, we're going to have two more folders, Train and Test. Now, the original dataset came with 3 folders, Evaluation, Training, and Validation, but we don't have any need for 3 separate datasets. So what we're going to do is just use the Training folder as the train set and the Validation folder as the test or validation set. We'll ignore the evaluation folder. Inside the train and test folders, we need to have a folder for each class. So you can see here that I've created 2 folders inside each of the train and test folders, food and non-food. Next, it's just a matter of moving the images. Moving is better than copying in this case, since we don't want to take up too much space and waste time replicating the data on disk. So you can see here that I'm taking all the files that start with 0 and end in JPEG and moving these to the corresponding non-food folders. I'm taking all the files that start with a 1 and end in JPEG and moving these to the corresponding food folders. Next, I'm going to specify the transformations to perform on both the train and test sets. As usual, you should try to play around with these data augmentation parameters to see what effects they may have, if any. You'll notice that the final transformation I apply happens to both the train and test sets. It's a normalize, which, as you might expect, does normalization, and I've specified what appears to be just a bunch of random numbers. So what are these random numbers and why are they there? Well, you'll have to remember that these are pre-trained networks with very specific weights. So we can't just pass in any image in any way we want into this neural network. we have to transform our image in the same way that the original authors of the neural network did. Otherwise, our input won't make any sense. So this is more or less like that. There are some additional details that I don't want to get into. Now you'll notice that there are many more transformations we're applying to the test set, which may seem odd. You might think, why are we applying data augmentation to the test set? And actually, we're not. So these transformations are static transformations. They don't augment the data. They're just necessary for the neural network to work. So the first transformation, which of course has to be applied to both datasets, is the resize. CNNs work on image batches of constant size. So first we'll resize to 256 by 256. After that, we crop the image to be of size 224 by 224. Okay, so that's why we have some transformations on the test set. Now you notice that the trained data has a few additional steps in between, so random rotation, color jitter, and so forth. As mentioned, you should feel free to play around with these, change the order, and so on. Next, we create our image folder datasets. This is pretty trivial. We pass in the paths to the image files and the transforms that we just created. Next, we create our data loader objects as usual. Next, we define our model. So this is going to look very different from what you're used to. First, we grab the VGG16 model, which is located in the Torch Vision Models module. We set pre-trained equal to true because we want pre-trained weights and not random weights. Next, we freeze the weights so that these weights are not updated during training. We can accomplish this simply by looping over the model parameters one by one and setting the requires grad attribute to false. Next, we print the model. So you can see that it's a very large model. Importantly though, it has a structure we've seen before. So the first part is a sequential that wraps all the convolution and pooling layers. As you can see, this is attached to an attribute called features. Next, we have an average pool 2D. And finally, we have another sequential that wraps the dense layers. And this is attached to an attribute called classifier. So if we print out model.classifier, we see just the ANN part of the CNN. This is the part we want to get rid of because we want to attach our own head. So next we're going to get the number of features that are output from the first part of the model and call that n features. We need this because it's going to be the number of inputs into our head. So we can get this by calling classifier of 0, which gives us the first layer, and then calling the attribute in features. So we have 25,088 features. Next, we're going to create our own classifier, which will just be a regular linear layer, logistic regression. And we'll assign this to the classifier attribute to replace the old one. So if we print the model again, we can see that the classifier attribute now refers to our own linear layer. And next, we move the model to the GPU as usual. Actually, after this, everything is the same as before. So we create a loss and optimizer, we create the training function, we call the training function, we look at the loss per iteration, and we calculate the accuracy. And these are the results. So we get 99% accuracy on this large image dataset using transfer learning.